followed by Benham Dostray, who is our in-house CFD specialist and engineer, who will discuss the more technical side of today's presentation. ENA2 is an engineering consulting firm based in Calgary, Alberta. Since 2008, we've provided services in a variety of industries, including energy, manufacturing, aviation, marine, and automotive. We also are a certified reseller partner of Dassault Systems' SIMULIA brand of products, and we are a certified training center. So whenever companies buy software from us, we're able to train their employees and ensure that they have the skills and proficiency required to use the software. ENA2 also works in a variety of engineering disciplines, including acoustics engineering, civil structural, mechanical, and pipeline and process engineering. We also work in product development and FEA and CFD analyses. On the top timeline, you'll see the Dassault Systems SIMULIA brand of products. Starting from the left, we have SIMULIA Abacus. And Abacus is the industry leader of finite element analysis software because of its ability to model nonlinear physical behavior. Following Abacus, we have FeeSafe. And FeeSafe is a fatigue analysis software, and it can also model cyclic loading. We also have iSight, and iSight is a workflow optimization software. And finally, Tosca. And Tosca is a structural optimization software. So with Tosca, you're able to cut back material expenditure while maintaining structural integrity. And this material expenditure cutback has multiple cost benefits. Moving to the CFD software, we have XFLow and PowerFlow, which are both high fidelity Lattice Boltzmann based software. And we also have FMK. And FMK is a mainstream 3D solver in 3D Experience platform. Now I would like to pass the presentation on to Benham to discuss the more technical side of today's presentation.
Thank you, Aaron. In the followings, first I'm going to overview the SIMULIA fluid portfolio. Next, I'm going to talk about SIMULIA XFLow key features. Later, shortly, I will talk about flow simulation approaches and porous medium, and then show the SIMULIA XFLow porous medium module. I will end up my presentation by a case study. SIMULIA Fluids was born in 2009 by incorporating CFD capability to Abacus. Abacus is a finite element solver used usually for stress and strain analysis. However, the Dassault system incorporated CFD capability to do fluid-solid interaction analysis there as well. So in 2014, a mainstream CFD software is added on 3D Experience platform. We call it FMK. FMK is a finite volume-based solver. In 2016, SIMULIA acquired XFLow from Nextimate Dynamics. XFLow is a high-fidelity Lattice Boltzmann-based solver. In 2017, another acquisition was from EXA. SIMULIA acquired PowerFlow, which is a Lattice Boltzmann-based solver from EXA. Here that I'm talking with you, SIMULIA has one mainstream CFD solver and two high-fidelity solvers, FMK, XFLow, and PowerFlow. Like any other softwares, XFLow has some features that distinguish it with other software packages. I'm going to only talk about that key features. First, XFLow is developed based on Lattice Boltzmann technology. That means XFLow solved Lattice Boltzmann equation instead of Navier-Stokes equation. The discrete form of Lattice Boltzmann equation is shown there. However, before interpreting that equation, please look at the picture in the right-hand side. The Lattice Boltzmann equation will be solved in mesoscopic scale. The mesoscopic scale is a scale between microscopic scale, macroscopic scale, which Navier-Stokes equation is solved in, and microscopic scale that we use molecular simulation. So in the mesoscopic scale, so again, we will have a space discretization we call it mesh or voxel. However, inside that voxel, we discretize the velocity of the group of the particles in a specific direction. So here those arrows show the velocity, discrete velocity direction that we call it C. So come back to Lattice-Boltzmann equation. F is the distribution function, or let's say the density of the group of particles. So the density of the group of particle with velocity Ci at location x plus Ci delta t at t plus delta t time is equal to its distribution or density at time t and location x plus any effect from particle collision. The omega there is a particle collision term. Another key feature is its effortless space discretization. The discretization in XFLow is very simple. The software generates cubic elements, and as we all know, the generating cubic elements very easy compared to other complicated mesh. Another key feature is its robust handling of complex geometry. So the mesh in Lattice-Boltzmann method or XFLow is cubics. The software mesh everywhere, both solid and liquid. The software, however, solves those nodes or mesh that the flow is passing through, to solve the Lattice-Boltzmann equation there, and set off those meshes in the solid region. It doesn't matter where the solid region is, so it just set up those meshes. So imagine if the solid is moving, it understands the solid region, set it up, and only solve it for the region. That's why it is very, very efficient in handling of complex geometry. As a result, you can see in these two pictures, so XFLow is very efficient in rigid body dynamics, direct free motion, and true rotation. Another feature is strong scalability. So Lattice-Boltzmann, discrete form of Lattice-Boltzmann equation is easy to solve compared to a Navier-Stokes equation, and as a result, it's very easy to parallelize the code. So accordingly, the scalability is also strong. Another key feature is that XFLow is capable to simulate on GPU. GPU is another processor in our computers that is very powerful. As an estimate, I can say that a good GPU capability to simulate is almost 1,000 times faster than a normal cores or CPU. Before talking about the porous medium module of XFLow, let's start with some definition. Porous medium, we call porous medium any solid containing void spaces or an object with gaps too fine to mesh. Looking at this radiator, you can see that those gaps are too fine to actually solve direct flow, to solve direct flow equations there. So as a result, we consider the whole object as a porous zone and use the porous zone techniques that I'm going to talk about later. Two approaches to simulate flow in porous medium. First, porous case simulation. So in the porous case simulation, we have the topology of the object. We know where the void is, where the solid or the matrix is, and solve the equation, either an Navier-Stokes equation or Lattice-Boltzmann equation in the fluid that is flowing in the void region. However, we use porous scale simulation to obtain, for example, we take characteristics of the flow and porous material, like porosity, relative permeability, wettability, etc. It requires 3D network structure of the porous material. It is computationally expensive because those void spaces are very fine. So maybe in the order of 10 to the power of -6 or even finer. And as a result, is not a practical technique for larger. For large rain, however, we have another. We use another technique that we consider the porous zone, the fluid region, where energy is removed as a pressure drop. So we consider the whole porous medium as a porous zone, which is a fluid region. However, in this fluid region, we have a pressure drop term that usually is a polynomial of the first order or the second order. For example, Darcy's law used the first order polynomial with respect to velocity, and Fornheimer law used the second order polynomial. So when we are talking about porous media module or in any software, we are actually talking about the porous zone approach. In the porous zone approach, the pressure drop term will be added to the governing equation as a source term. The velocity and the pressure drop equations are volume average velocity, not superficial velocity. Imagine the porous medium. So here is the porous medium. The real velocity of the fluid in the voids is US, which we call it superficial velocity. However, since we consider the whole region as a fluid region, we should use UV, the volume average velocity, instead of US. It is unable to distinguish pore and matrix here, because it is actually obvious because we consider the whole domain as a fluid region. We don't see any matrix here. We only see the fluid here, but however, with different velocity term. The question is, so what is the pressure drop form in XFLow? The pressure drop in a porous medium has the following form in XFLow. Again, it uses a second order polynomial with respect to velocity. Mu is the viscosity of the fluid, L is the thickness of the porous medium, K is the permeability, U is the velocity, C epsilon is the Ergen coefficient, and rho is the density of the fluid. Graphic user interface from XFLow is depicted here. When you choose your geometry or import your geometry, the software asks, for example, asks you to define the region as a porous zone, for example. So here, under boundary condition, you can define your region as a porous volume. The software asks if the porosity type is isotropic or anisotropic. So in isotropic, the direction is not important. So it asks the permeability coefficient and Ergen equation just once. However, in anisotropic form, you need to define the permeability coefficient and Ergen coefficient in 3 dimensions. How to find out the permeability and Ergen coefficient? We usually use the pressure drop data, which is obtained from manufacturer, literature, experiments, or porous scale simulation. And the data of delta P with respect to U is shown there, for example. We fit a curve, which is in the form of second order polynomial. This second order polynomial has 2 constants, C1 and C2. You can find C1 and C2 with the fitting curve approaches, for example, from Excel. You compare it with the Darcy-Ergen equation that is shown below, and as a result, you can easily find the permeability coefficient and Ergen coefficient. Just as a note that all the variables in XFLow is expressed in SI unit. K has the unit of meter square, and C epsilon is dimension. So, as a summary, you need to have the permeability and Ergen coefficient ready. So you import your geometry, you define your geometry as a porous zone, and you define the permeability and Ergen coefficient of your porous medium. That's all the story here in XFLow, even in other softwares. As a case study, I chose a simple geometry. We have a channel here, and a 2D channel actually, and the porous medium is mounted there. The flow with the velocity of 0.1 meter per second enters to the channel and also passes through the porous medium. The dimension of the channel and porous medium is depicted there. Switch to XFLow graphic user interface. So you can see the project tree in the left-hand side. The main part that we define our case is here. We start from left to right. There is a message view part in the left bottom side, and also on the right-hand side, you can see the graphic view. So let's just start by importing the geometry. I have two geometry, one channel and another porous medium. So the big is a channel, and the target role here is simulation. You can even import any geometry for post-processing as well. So the channel is imported. Generally in XFLow or generally a geometry or a surface is defined by its normal direction. So in XFLow, the normal direction should be toward the fluid. So here, by right-clicking on the geometry, I can change the normal direction of my imported geometry. So the name of this geometry is shape. The boundary condition here is wall, but we can define another boundary conditions as well. So we select that surface by right-clicking and applying boundary conditions. We can do the same for the outlet. Come back to the left-hand side, rename the surface as outlet. So the boundary condition type in that region is outlet. You can choose pressure outlet. The pressure is 0 Pascal, the gauge pressure. Switch to inlet. You select the inlet, rename it to inlet. The boundary condition is inlet velocity type, maybe. The velocity in the x direction is positive 0.1 meter per second. And other surfaces, of course, are wall, and the boundary condition type is wall. So we already defined this geometry. However, I need to change the direction, the normal direction of the surface inward, because the flow is passing through the channel. Next, we are going to import the porous media. The normal direction of the porous media in XFLow should be outward. It is a rule. So the name of the shape is small. The boundary condition should be now the porous volume. So porosity type, let's select isotropic, and let's define permeability coefficient as 10 to the power -6 and area coefficient 0 as an example. So we are done with the geometry. Let's go to the project tree, start with the environment to define the case. Our simulation is 2D. We have a single phase analysis. The execution will be on CPU. It is an internal simulation. The thermal model is isothermal, of course. So for defining turbulence model, I need to talk about the turbulence model in XFLow. So any simulation in XFLow is transient first. We don't have steady state analysis like finite volume-based software packages. And the turbulence model, the default turbulence model is a larger simulation in XFLow. However, so in larger simulation, the software solved the larger Ds directly. However, to model the small eddies, the software used one of those models, Smok-Warinsky, dynamic Smok-Warinsky, and so on. The default model is wall adapting local eddy shown here, the automatic one. So the turbulence model, we choose automatic, which is while adapting. And the turbulence regulation is off. We don't have acoustic analysis. We don't have scalar transport. Coming to environment, low attributes. There is no acceleration law is minus 9.81. The initial condition can be user-defined or from the simulation. Here, the user-defined is selected. And you can define the reference velocity and so on. Switching to the material tab, here is the air properties. The geometry is already defined. Coming to simulation, the simulation time maybe 5 seconds. It is it can be automatic or custom. If you choose automatic, you need to define the current number here. Okay, here is the interesting part, the mesh part. You need to only define the mesh resolution. We don't have very complex mesh geometry creation in XFLow. You define the resolution, but you can also later refine your mesh in here static file, or you can use adaptive define. So here is the storage data by 10 Hertz means 10 frames per second. 100 means 100 frames per second. Since the simulation is 5 seconds, 10 Hertz means 50 frames. You can save the average field or other options. Output format is a native XFLow format here, but you can use the famous VTK format. Here are the fields to save. You can even define the pressure filters, probes, surface integral, volume integrals, and so on. So we save the case, we start the simulation. So the software first mesh the case, then start the simulation. After starting the simulation, we will switch to post-processing tab. Okay, the simulation is started. The velocity contours are showing there at different time. Switch to post-processing. Here is the interpolation of interpolation form, of course. So you can see the domain structure is all cubes. You can visualize the volumetric field. You can see the surface information. You can define cutting planes as we have done it here. So the cutting planes, and in this cutting planes, you can see the velocity or pressure or other variables. However, here the contours are in the fluid region. By going to geometry and turning out the shape, the porous media, you can see the contours inside the porous medium as well. Okay. Okay, that's all. It is all we can do in simulating the case. For further contacts, you can contact me as a CFD specialist and also Nuria Sarsu as our director of projects. Thank you very much for joining our webinar, and hope to see you in our next webinars later.